right, let's do some pH problems here. All right, the first problem that I'd like to go over with you guys is calculate the pH of an HNO3 solution having a hydrogen ion concentration of 0.76 molar. So HNO3 is a strong acid. There are 6 strong acids. Okay, do you know which 6 are those? Okay, one is HNO3. What's the other one? Okay, so you should know these 6 acids as them being strong. So what does that mean when they're strong? They give 100% H3O+, 100%. So when you see these acids and you know that they're strong acids, you can plug it in straight to the pH equation. So what is the pH equation? It's going to be minus the log of your hydrogen ion concentration. But this is a strong acid, right? It's one of these 6 strong acids, so you can just plug that in here. Okay, so no ice table. Okay, no anything. Okay, you just plug it in straight. And what's the answer to this? Minus the log of 0.76. About 0.12. 0.12. So also remember pH does not have any units. Also pOH does not have any units. Okay? And we want to remember this relationship: pH, the power of hydrogen as the base, plus the power of OH, power of hydrogen as the acid, plus the power of OH as the base, equals 14. So it's a strong acid, just plug it in. Okay, that's the take-home point. Okay, how do you know it's a strong acid? Okay, it's one of these 6. Any other acids, you can't do that. You have to use an ice table. Okay, any other acid, you'll have to use an ice table. How about this? The pH of a certain range of orange juice is 3.33. They call that the pH. Calculate the hydrogen ion concentration. So pH is minus the log of H3O+. Okay, so notice that I use them interchangeably. And so what we have here is our pH is 3.33. Okay, equals minus the log of the hydrogen ion concentration. So to get the hydrogen ion concentration, you're going to back calculate. Okay, and that's the anti-log. The anti-log is 10 to the power of minus pH. And this is going to be 10 to the power of minus 3.33. So what is the anti-log on our calculator? Okay. So you're going to do shift and then the log, or second and the log. Okay. This is how you flip back and forth. pH minus the log of hydrogen ion concentration. Hydrogen ion concentration is 10 to the power of minus the pH. Okay, this is how we go back and forth between the two. And I'm getting 0.000468, big M. So I noticed in the test that while I was grading them, that a lot of students didn't put the proper units. And it's still an issue, but you need to put units. Okay, it's just, the right thing to do. 0.000467. Okay, so the units here are molar. It's kind of like if you're a doctor and you do surgery, or you're a dentist and you do the cavity removal, and then you walk out and leave. Okay, and that's it. And then you tell the guy to leave. You tell the patient to go. You got to stitch them up. You got to clean it. You got to do all the post-op. Okay, to me, putting a number by itself is kind of the same thing. So, every number must have units. That's just the right scientific way of doing things. So, the lesson is always put units. All right, the OH concentration of a blood sample is 2.57 times 10 to the minus 7. What is the pH of blood? Okay, so anybody here a biology major? Oh yes, you're a biology major. Okay. So a lot of biology majors, they have to work with blood and stuff. Also in biochemistry, they do a lot of blood work. So your blood has a pH, okay? So, but they're asking us to calculate the pH, but they're giving us the OH minus concentration. OH minus, this is the hydroxide ion concentration. So how will we do this? They're giving us the pH. They're not giving us the hydrogen ion concentration. They're giving the OH minus concentration. So instead of calculating the OH minus, why don't we calculate instead of calculating the H plus concentration, why don't we calculate the POH? That's what I'm trying to say. Calculate the POH, which is minus the log of 2.5 times 10 to the minus 7. So that's going to be 6.60. Okay, so that's the POH. Okay, how will we get the pH? What do we need to do? Very good. Okay, we'll take 14 minus 6.60, and that is a pH of around 7.4. Okay. Because you have to remember this relationship, pH plus POH is equal to 14. What's the right? So POH is 6.6, the pH is 7.4. That's right. Okay, which is more acidic, a solution where the H plus concentration is 2.5 times 10 to the minus 3 molar, or a solution with a POH of 11.6. Okay, so we have two solutions here. I'll call this solution 1, and I'll call this solution 2. So what do you think is more acidic? More acidic means more H plus. Isn't this correct? Okay, if you're more acidic, you have more H plus in the solution. So the higher the H plus concentration, the more acidic it is. Okay. But what do we know about the higher the H plus concentration? What does that also imply? Okay, it implies a lower pH. Okay, that's how that works. Okay, it's because pH is minus the log of H plus. Okay, so what we can do here is calculate the we can calculate the pH here. What's the pH of solution 2? 14 minus 11.6, which is 2.4. Okay, so no units. No units on pH or POH because it's a scale. And then we'll do the pH of solution 1, which is minus the log of 2.5 times 10 to the minus 3. And that's 2.60. Okay, so which is more acidic? A pH of 2.6 or a pH of 2.4? 2.4 is the right answer. Okay, 2.4. You need to remember this relationship. The lower the pH, the more acidic it is. Some basic pH, POH considerations, okay? Excuse me. You guys know the pH scale? Okay, what is pH 7? neutral. pH 7 is neutral. Actually, if you look at this table, if you look at pH 7, okay, they have the same concentration of OH minus and H plus. Okay, but as you go lower and lower, okay, you see how the pH goes from 6, 5, 4, 3, 2, 1. What happens to your concentration? Bigger, 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 bigger. Okay, so again, as your pH goes down, that implies the H plus is going up, more acidic. And the reason why is just the math minus the log of the power. This P stands for power. Okay, so let's move on here. All right, so just in case you guys forgot, I'd like for you to know these. These are the 6 strong acids, and what I want you to know is that they're strong. Look at the arrows here. Okay, what do you see about the arrows? Yeah, they're all pointing towards the product side. They're all pointing in one direction. Okay, very little, Royce, very little goes this way. In fact, it's like negligible. Okay, very little goes the other way. Okay, like 100% ionization for these 6 strong acids. Which means, number 1, no ice table. Okay, to get the pH, what do you need to do? You plug it into the negative log, okay, because we assume it's 100% or 99%, very close to 100% ionized. Okay, any other acid that's not on this list, you can't do that. Okay, any other acid that's not on this list is considered a weak acid. Yes, so you can't do that. Also, the Ka, that equilibrium constant, is very large. It's 1. Okay, a very large Ka. If I give you $1 million, are you moving forward or backwards? I give you $1 million, you're moving forward. So if you have a Ka of 1 million, the reaction is facing forward. Okay. Remember, there's no units on the Ks. Okay. Right, so we're going to contrast that with some of the acids that are on page 11. These are the weak acids. So what is it about the arrows on the weak acids? They're at an equilibrium. Perfect. Okay. So it's not 100% completion. It's not 100% ionization. Okay, that's number 1. So number 2, we have to use an ice table to get pH. We cannot plug it in, Royce, into the pH equation. Why is that? Because they're weak and it's not in going to 100% completion. That's correct. Okay. Calculate. Okay, what else do we need besides the ice table? Okay, we can't just plug it in, so we need the Ka. Okay, so I'll give that to you on the exam. So some of these acids have a Ka that's given to us, and you notice that the Kas are small. Okay, Ka is small, so we're going to say less than 1. Okay, this is the situation for what we are calling weak acids. Well, how do you know it's a weak acid? How do we know I give you an acid on the exam and it's weak? It's an equilibrium, but what else?
It's not one of the 6.
It's not one of the 6. That's correct. All right, so any other acid, I'll give you the Ka. Okay, like I do here. And then you have to use the ice table. Right, so we'll do a lot of ice tables, and also this problem set has a lot of ice tables in there as well. Okay. All right, now let's talk about ice tables for weak acids. So we're going to do a lot of these in chapter 15 and chapter 16. So first thing I want to tell you is this, okay? So we're not going to have the quadratic, but there are situations where you may need to use the quadratic. And when you use the quadratic or not is dependent on what's called the low ionization assumption. So the threshold is 5%. Okay, so less than 5% ionization, you can use this assumption. You're going to plug it into this formula. Okay, you'll take X, which is what we get from the ice table. Remember, weak acids need an ice table because they do not go to 100%. Okay, you're going to divide it by the concentration in the bottle or the concentration that's given in the problem. And then you multiply it by 100 to get a percent. If this percentage is less than 5% ionization, that means less than 5% going this way, then you can use this assumption and you can avoid the quadratic on your ice table. Okay. You remember there's a problem I did the last chapter where we did the quadratic, but I told you like this is not on the exam. Well, this is the formalization where if this is less than 5% going in the forward direction for the acid or the base, then you can get away with not using the quadratic, using the low ionization assumption. Okay, what does all this mean? Okay, this will mean something when we do this problem together. Again, weak acids. Weak acids, we need an ice table, but we can do the low ionization assumption. All right, so I want you guys to do this problem with me because this is going to be the setup for what we'll do many, many, many times over in 15 and 16. So what is the pH of 0.122 molar monoprotic acid whose Ka is 5.7 times 10 to the minus 4? Ka less than 1. It's given to us in the problem. We need to find the pH. So the first thing we want to do is write the equation. Okay, whether it's any acid, this is just HA, the A stands for acid. The first thing you want to do is write your equation. So this is what I want you to do on the exam. Okay. So what do acids do? Okay, acids donate protons. Okay, this H2O picks up that proton, and then we get H3O plus and A minus. Okay, this is generic because we can, we'll do it with real acids, but this is the first thing you need to write. It's not a strong acid because it's not one of the 6. And this is the first equation that you have to write because this acid is going to react with water in the solvent. And this one has a Ka of 5.7 times 10 to the minus 4. Okay. Right. So if I draw a bottle of 0.122 molar HA, if I have a bottle of 0.122 molar HA, some of this bottle does not contain HA. What else is in the bottle? Correct, it's the solvent, but what else? Not just HA, but what else? Okay, this HA is going to react with the water to give you proton and A minus. Right, so we'll do our ice table now. When you do your ice table, you can avoid the liquids. Okay, 0.122. Okay, 0, 0. Okay, this will be minus x, plus x, plus x. So at equilibrium, it will be 0.122 minus x, plus x, and plus x. Right, so at equilibrium, we'll plug it into the equilibrium expression, which is Ka is equal to the concentration of H3O plus times the concentration of A minus divided by HA. Okay, we'll plug in these values. Right, so the Ka is given to us as 5.7 times 10 to the minus 4. Okay, what is H3O plus at equilibrium? X. What is A minus at equilibrium? X. What is X times X? What is HA at equilibrium? 0.122 minus X. Okay, so now this is what you'll do on your test or an exam. Okay, we're going to assume X is small. Okay, this is called the low ionization assumption. Okay, assume X is small. That means very little goes in the forward direction. The threshold is 5%. If it's over 5%, this assumption fails. So assume X is small, so 0.122 minus X is about 0.122. So this means 5.7 times 10 to the minus 4 equals X squared divided by 0.122. So this is the low ionization assumption. Assume X is small. And now we'll solve for X here. Okay, we'll take that 0.122, move it that side. Okay, we'll take the square root. That'd be X. Alright, so what's 5.7 times 10 to the minus 4 times 0.122? Square root that. We do this for the weak acids. Square root. I'm getting 0.00834 units. Big M, 0.00834. What does this X mean, though? What is this X? All right, so this X is the concentration of H3O plus. This X is the concentration of A minus, and 0.122 minus that X is the concentration of HA, whose original concentration is 0.122. So it's asking us to find the pH. So what is the equation for our pH? We know the formula for pH is minus the log of the hydrogen ion concentration. And what is the hydrogen ion concentration? X. What is X? 0.00834. And what is this on our calculator? 2.07, 2.08. Okay. And this is the answer, but let's check our assumption. Okay. Remember, we made a big assumption. We just removed that X saying that it's small and very little is going in this direction. Okay, what's the threshold? Threshold is 5%, so we're going to check our assumption. So we'll use this equation. What's X? Okay, X is 0.00834. Okay, what's the initial concentration of the acid? What's the concentration of the acid in the bottle, or given to us in the problem? 0.122. Okay, multiply this by 100, and let's see what we get. 6.8% ionization. Does our assumption work? Okay, what was the threshold? 5. Okay, so if it's less than 5% ionization, less than 5%, then this is okay to go from here to here. And this is 6.8%. So we can't use this assumption, so we'll have to use the quadratic. Okay? On the exam, you can do this because there's no quadratic on the exam. Okay, why can't we use this for this specific problem? Because it's 6.8, greater than 5%, yeah. So I went ahead and did that on page 13, but again, like I said, you don't have the quadratic on your test. Right, so I went ahead and solved for that. Okay, using the quadratic. All right, page 14, I'll go over it very quickly. I did an ice table on water. This is just for fun. So I did the exact same thing, and I found water. This is the equilibrium for water. Doing the exact same thing we did before in the previous problem. I found it to be 0.0000018%. So very little water ionizes to give you as a source of H3O plus acid or OH minus base. And I remember this statistic. I remember reading it. And very little things stick in my mind. You know, a lot of things go in the ear, out the other. But I remember this. So as it goes in this textbook, for every 1 trillion water molecules, one of them will go here and give you H plus and OH minus. 1 out of every trillion. It was mind-boggling to me when I read that. But, so number 1, water is a source of H plus and OH minus. It's a source of acid and base. But I think in biochemistry, that's important, okay? Because inside the cell, we know water participates in a lot of reactions. So I just did that ice table for water, where water self-protonates itself to give you H3O plus and OH minus. Very, very little. If it's very pure, very little gives you H plus and very little gives you OH minus. But in biochem or some of the chemistry subjects in biology, that small amount that goes that way is still very important. All right, let's move on here to page 15. So let's just review here. For strong acids, okay, what do we have to do with them? Okay, you mentioned it, Royce. We just plug it in straight into the pH equation. All right, so what do we plug in those straight into the pH equation? You plug it into negative log for these acids. Okay, there's 6 of them. Okay, perchloric acid, nitric acid, hydroiodic acid, hydrobromic acid, sulfuric acid, HCl. Okay. So like I said before, here, if you see that, just plug in, as Royce, our classmate, told us. No ice table. 100% ionization. And plug into pH is minus the log of H plus. What about weak acids? Okay, so weak acids are anything like you mentioned, Samantha, anything that's not the 6. So let me give you a stereotypical example. That would be acetic acid, or any any acid that's not this. Okay, what do we do for weak acids to find the pH? Okay, here we have to use the ice table. And here we can use the low ionization assumption to get the pH. Okay? Low ionization assumption. Remember the threshold is 5%. Okay, this is a good source of H+. This is a weak source of H+. Okay, these acids are weak sources of protons. These acids are very strong sources of protons. Right, the next one on our list are the strong bases. Okay, so what are strong bases? Okay, anything that has OH minus. Okay, OH minus. These are the group 1 and group 2 hydroxides. Okay, NaOH, KOH, okay, LiOH, okay? So anything that gives you OH minus is a strong base, okay? And here you're looking for the hydroxides, okay? They in water give you hydroxide ion. So again, like we're talking about NaOH, KOH. Okay, this is called acetic acid. Okay. So what do we do with our strong bases? Okay, we have no ice table. Okay, 100% ionization to OH minus. Okay, how will we get the pH? What will we calculate first? Not pH, but what will we calculate first? We can't calculate the pH. What should we calculate? It's 100% source of OH minus. What should we calculate? So here we calculate the pH because it's 100% source of H+, the strong acids. Here, what will we calculate first to get the pH? We don't calculate the pH first. What do we calculate? We will calculate the POH. Okay, and from there we will get pH. And then finally we have the weak bases. Okay. So anything that's not OH minus is a weak base. All right, so as some examples, you can see page 17 of our notes. Another classic example, a very stereotypical example, is ammonia. So many people don't know this, that ammonia, NH3, is a source of OH minus. So what do we do here for the weak base? Okay, here we have to use an ice table. Here we can use the low ionization assumption. And then before we calculate pH, what do we have to calculate? Okay, we will calculate POH, and then from POH we will get pH. So this is what we need to do. Okay. So let's look at ammonia here, NH3. Check the time. Okay. So ammonia is actually a weak base. And here you can see in the equation, all right, so ammonia is a source of OH minus. Okay, what do these bases do? Okay, the bases react with water. The acids react with water, they give the proton. The bases react with water, they take the proton. Okay, so it's going to take a proton, and when it takes the proton, it becomes the conjugate acid NH4+. This is the ammonium ion. This is the base and its conjugate acid. H2O gives up the proton, so when it gives up the proton, it becomes the acid, and then as it gives up the proton, it gets transformed to OH minus, and that's the conjugate base. Okay, so this is the KB. Okay, not Ka, KB. The reason why it's KB is because this is reacting with water to give you OH minus. If we're talking about Ka, the acid will react with water to give you H plus. That is Ka. But the base reacting with water to give you OH minus, this is Kb. Okay. The acid reacting with water will give you H plus, that's Ka. Acid reacting with water giving you H plus, that's Ka. Okay. Your base reacting with water to give you OH minus and the conjugate, that's Kb. Kb. So Ka, Kb. And let's not forget Ka times Kb is 1.00 times 10 to the minus 14. Okay. Which is actually Kw. So it says here, calculate the pH of a 0.018 molar solution of barium hydroxide. So what do we know about barium hydroxide? Is it a strong acid? Is it a weak acid? Is it a strong base? Or is it a weak base? Okay, hydroxide. Okay, barium hydroxide in solution is barium ion plus OH minus. Okay. So this is actually a strong base. Okay, why is it a strong base? Because of the OH. Okay. So barium hydroxide in water actually dissociates into barium ion and hydroxide ion. And we will balance this to give it 2. So it's not a source of 1 OH, but how many OHs? Okay, 2 OHs. So how will we get the pH here? Well, we don't calculate the pH first. What will we calculate? Okay, and it's a strong base, Susanna, so we'll plug that in here. It's a strong base, so you can plug it straight in. Just like the strong acid, we plug into pH. The strong base, we plug into what? POH. Okay, this is a POH. But this is actually incorrect because how many OHs are there? So we actually have to multiply this by 2. Okay. Because 0.018 molar barium hydroxide, when it dissociates into water, gives you barium ion and 2, not 1 but 2. So we're going to take this and multiply it by 2. So what is minus the log of 0.036? Okay, remember, we multiply it by 2 because this source is 2OH minus. So what's minus the log of 0.036? .44. And what is the pH that corresponds to that POH? Take 14 minus that, and what do you get? .56. Okay, that's a very, very basic pH. Okay. That's what you do for strong bases. What do you do with weak bases? Ice table. What do you do with weak acids? Ice table. Okay, what do you do with strong acids? Plug it into the pH. Okay, what do you do with strong bases? Plug it into the POH. Okay, what are your strong bases? Look for OH minus. Okay, look for OH minus. All right, so let us, let's go back here. All right, let's do a KB problem. If I can finish this, and we'll finish this chapter by Monday. Yes, okay, Monday. All right, calculate the pH of a 0.26 molar methylamine solution. So one thing I should tell you is that the amines are weak bases. Okay, kind of like ammonia. The amines, which is one of the functional groups that you'll learn if you take organic chemistry. Okay, that's a weak base. Right? So methylamine has this formula here. Okay, I'll give you that formula. Okay, you do not have to memorize it. Right, so what is the Kb? Not Ka, Kb. So for a Kb, it's going to react with water. Okay, water will donate the proton and give you OH minus plus CH3 and H3 plus. Okay. And is this Ka or Kb? This is Kb because it's reacting with water to give you OH minus, so this is the weak base. And the Kb of methylamine, I'll give that to you as well. It's 4.4 times 10 to the minus 4. Okay, so I'll give you the formula for methylamine. I'll give you the Kb. Okay, I can also give you the Ka. Don't forget Ka times Kb is equal to Kw. All right, so we have a bottle that's 0.26 molar. Okay, methylamine. But that bottle of 0.26 molar methylamine does not contain methylamine by itself. What else does it contain? Okay, water, but what else does it contain? OH minus, and what else does it contain? CH3 and H3 plus. Methyl ammonium is what this is called. All right, so we're going to take our ice table 0.26. Okay, water is a liquid, so we can put a big X on it. Okay, 0, 0. This will be minus X, plus X, and plus X. So this is 0.26 minus X, plus X, and plus X. Okay, we'll plug that into the Kb. Okay, why did I put water in here? Because it's a liquid. So Kb is 4.4 times 10 to the minus 4. Okay, OH minus is X. CH3 and H3 plus is X. X times X is X squared. This is 0.26 minus X. Okay, so we will assume X is small here. So you can do this on the exam. So 0.26 minus X is about 0.26. So 4.4 times 10 to the minus 4 equals X squared divided by 0.26. 4.4 times 10 to the minus 4 times 0.26. Okay, well, square root of that is equal to X. So what does X equal to? Okay, square root it. I'm getting 0.0107. Did you get that? 0.0107. Okay, molar. But what does that X really symbolize? Okay, this X is this X, which is the concentration of OH minus. So before calculating pH, let's calculate the POH. So how will we do that? POH is equal to minus the log the concentration of OH minus. Okay, the OH minus is X. X is 0.0107. And what is that on our calculator quickly? About 1.97. So what will that make the pH? Okay, 14 minus that. And what's 14 minus 1.97? 14 minus 1.97 is 12.03. Okay. So that is using the low ionization assumption for a weak base. So we will wrap this up here on Monday, and then Wednesday we'll start chapter 16. So the test is not the 31st. I will push the date back until we finish chapter 16. So Monday and Tuesday we don't have lab. Work on your problem set. Okay.
Was it worksheet today also for chapter 15?
I can push that back. If you have it uploaded, I'll put the points in, but I can push it to like Wednesday or so.